Welcome to this video about current and how electrons move within conductors, and to show you how conductors actually displace their electrons. I've made these simple two sketches for you. Now in the first one we have a normal metallic bond. Metals are elements which are known for having a few electrons on their outer shell, and preferably they would get rid of them in order to achieve a sort of a noble gas configuration. Now that means every single atom in a metallic bond is naturally trying to get rid of its electrons, meaning there are a lot of electrons moving freely within your matter. Now in that metal, the random movement of it can't be described as a current going from one side to the next. It's a natural thing. However, if we apply voltage to that conductor, meaning we have a negative pole on one end and a positive pole on the other, an electric field is created within that wire. Now, the charges that are in a metal are electrons. They are negative charges. And in our previous chapter we've seen that if your electric field is going from positive to negative, which it always is, but it is affecting a negative charge, your Coulomb force will be in the opposite sense of the electric field in this case. Meaning all of your electrons will be moved from one side to the next. And as we've discussed, as they are moved, their electrical potential energy is used up, is converted into a different type of energy. What type of energy that is depends mostly on the consumer you're using, but heat will always be essentially generated as well alongside with it. Which leads us to amperage. The amount of charge that gets moved per second is what is defined as the amperage of the current. 1 ampere of current is essentially 1 Coulomb worth of charges. That is a whole lot of electrons, remember, because the elemental charge is very small. Is 1 Coulomb worth of charge moved per second in this case. And it leads us to this equation. For current, it is the amount of charge moved per second. So it also leads to a next thing, namely battery capacity. Batteries hold a certain amount of charge in it, and technically charge should be expressed in coulombs. However, if somebody's buying a battery, they would have absolutely no idea what an amount of coulombs worth of charge means. So they use an alternative unit for a battery capacity. It's often expressed as amp second, meaning how much amperage can it deliver for how many seconds. Although quite often they use amp hour as well, because a second is a bit short and hours is a more usable unit to figure that one out. Or, as can be used in certain batteries of, for instance, cell phones, we will often use milliamp hours, which is just 1/1000th of an amp that can be used for a certain amount of hours. So 1 amp second means 1 Coulomb of charge. That will not get you very far in this case. 1 amp hour means, well, 1 hour is 3600 seconds, so that would be 3600 coulombs worth of charge in that battery, and 1 milliamp hour would be 1/1000th of that, meaning 3.6 coulombs of charge. Now, imagine you have a battery that has a capacity of 100 amp hours. How long will it be able to provide you a 4 amp current to an electric circuit? Well, in this case, you take your 100 amp hours, you divide it by your amperage, in this case 4 amps, those two are dropped, you will be left with roughly 25 hours, which you can fill in on the dotted line here. You'll be left with about 24 hours worth of electricity out of that battery as well. Now, this is something you can do for yourself. You can actually find out what battery capacity your phone has in milliamp hours. Some older phones allow for it to still be opened up to actually have a look inside, although most modern devices these days no longer allow for that due to water resistance and everything. But you can look it up as well. You can find those specs and have an idea of how big the battery within your smartphone is. Now, if you want to know what battery life is like for your device, you could look at battery capacity, but that's definitely not the entire story. There are many different factors that will actually determine how long it can stay operational before it needs a charge. What are those things? Well, definitely in this case, there's several things you can fill in. So feel free to pause the video and fill in as you go along. But things like how powerful the processor is makes a big difference. Very powerful processors, as you can find in high-end devices, will use up quite a bit more energy. So that will have a big impact on it. Other things like your screen resolution. How many pixels are there on your screen? Very high resolutions of screens and screens with very high refresh rates will actually require a bit more power. How bright is your screen? Screen brightness will have a big role to play. Keeping Wi-Fi on all the time or turning it off. Keeping Bluetooth on all the time or actually turning it off are all things that will determine how long your phone or laptop or similar devices will last. Now, I want you to make these exercises for now concerning current, these two. They are fairly straightforward, but you will be receiving a feedback video on the solutions to these problems in a bit. If we're considering current, we also have to consider resistance in this case. If you apply voltage to a closed loop, current will flow from positive pole to the negative pole. However, the ratio at which of the voltage and the current it causes is actually a constant one, and you'll be discovering that during some lab work in this case. That constant is dependent on the wire you use, or the material you use, rather, that your conductor is made out of. So it is expressed in a new unit, the amount of volts needed per ampere of current it causes, and that is the new symbol, Greek letter omega, for Ohm's law. Ohm's law states that current is directly proportional with voltage, but inversely proportional to the resistance of the wire or the device that you use. In this case, there's plenty of ways you can show resistances in these schematics. Either you use blocks with the value of the resistance filled in, or these sort of sawtooth symbols that usually have the value of the resistance quite close to it. Now, we're fully aware that conducting wires have some resistance, albeit incredibly low, but we're going to be treating them as resistance 0 for our exercises. It's a bit of a simplification, but otherwise it would be quite long exercises to do so. Just consider them to be resistance 0 in this case. Now, a second question I ask here is the temperature of a resistor or conductor will also play a role in determining its resistance in this case. We already know that it's electrons that move inside of a metal, so will an increased temperature increase or decrease its resistance? Have a think about it. If it's electrons moving inside of your metal, the positive cores of your metal are going to be an obstruction to the electrons flowing by. Imagine how much more difficult it would be to do a sort of a obstruction track if those obstructions are moving around quickly. If you increase the temperature of a metal, those positive cores are going to be vibrating faster and faster and faster in this case, meaning it will actually be more difficult for your electrons to pass through. Ironically, although in quite a lot of cases you have learned that an increase in temperature means an increase in speed chemically, it is exactly the opposite for a conductor. So you can fill in the resistance increases as temperatures go up, because electrons will have a harder time flowing through the metallic roster, the metallic cores in this case. So cooling of your wires is required in this case. Now the next few exercises are again some that I will have you make, and you will get a feedback video on them shortly. In the next video we'll be discussing energy, power and efficiency in this case. I will see you then.